In this episode, we're going to make instance metadata feel simple, predictable, and worth your attention because it sits right at the intersection of convenience and danger in public cloud. Many beginners hear the word metadata and think it means harmless labels, like notes attached to a file, but instance metadata is more powerful than that. In many cloud environments, workloads can ask a special internal service questions about themselves, such as what instance they are, what region they are in, and sometimes what identity or credentials they can use to access other cloud resources. That design exists to make automation easier and to let applications discover information without hard-coding it. The security risk comes from the fact that attackers also love automation, and metadata services can become a fast path to privilege if a workload is compromised. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To understand why metadata exists, it helps to picture a cloud workload as a small computer that can be created, destroyed, or moved without anyone manually configuring every detail. When a new instance starts, it may need to know where it is running, what network settings it has, or what identity it should use to reach storage or messaging services. A metadata service provides those answers through a local interface that is meant to be reachable only from inside the instance, not from the public internet. This is a big convenience because it removes the need to store certain configuration details in files or to inject them through manual steps. It also reduces the need to distribute secrets in some designs because the instance can obtain temporary access tokens tied to its identity. In short, metadata is a helper mechanism for cloud-native automation. The term Instance Metadata API, is important because it highlights that this is not just a passive database of information. It is an interface that responds to requests. When something is an interface, it can be queried, and when it can be queried, it can also be abused if the wrong party gains the ability to make those requests. Metadata APIs are typically accessible at a special network location that is only reachable from inside the instance, often through a link local address that does not route outside. That sounds safe, but the safety depends on the assumption that only trusted code inside the instance will ever make those calls. In reality, if an attacker compromises an application running on the instance, the attacker's code is now inside the same trust boundary. At that point, the metadata API becomes a treasure map. A key beginner concept here is the idea of trust boundaries, because metadata services are designed around a trust boundary that is easy to misunderstand. The cloud provider treats the instance as a unit of isolation from other customers, but within the instance, the metadata service often assumes the instance itself is trusted. That means the metadata endpoint typically does not require a user password or interactive authentication, because the trust is based on network location and the idea of local access. For normal operations, that makes sense because the instance needs to get information without human involvement. For attackers, that is also perfect because once they gain local execution or can influence local requests, they can ask the metadata service questions without needing to crack a password. This is why metadata risk is often tied to the first compromise of a workload. It is also important to separate two kinds of metadata content: non-sensitive information and sensitive information. Non-sensitive information includes things like instance identifiers, region names, network interface details, and other facts that can help software configure itself. Sensitive information includes identity tokens, role credentials, or other temporary secrets that allow the instance to call cloud APIs with permissions. Not every metadata service exposes sensitive data in the same way, and settings can change what is available, but the pattern is what matters. If the metadata service can return credentials, then metadata becomes an access broker, not just an information source. Even if the credentials are temporary is still long enough for an attacker to do real damage. A short-lived key is still a key if it unlocks valuable doors for the next hour. Now let's connect this to why attackers love metadata in practical terms. Attackers want speed, stealth, and leverage, meaning they want to turn one small foothold into broader control without making a lot of noise. If they compromise a web application running on an instance, they may not have direct access to the cloud control plane yet, but the instance might. By querying metadata, an attacker can often retrieve a token that represents the instance's identity, and then use that token to call cloud services the instance is allowed to use. This can lead to actions like listing storage, reading secrets, creating new resources, or exploring the environment, depending on the permissions granted to that identity. The attacker has not broken cryptography or guessed a password. They have simply used a design feature in an unintended way. A classic scenario that helps you understand the risk without getting tool-specific is a request forgery problem, where an attacker can trick an application into making a network request to a location the attacker chooses. If the application can be influenced to request the metadata endpoint, then the attacker can receive the response indirectly. The scary part is that the application might think it is fetching an image or a web page, but it is actually fetching metadata. This kind of abuse works because metadata endpoints are local and do not look like public services, so developers may not anticipate that they need to block access to them from their application's request features. The underlying theme is that any feature that can fetch a URL can become a bridge to the metadata service if not constrained. That bridge is one of the main reasons metadata is a frequent topic in cloud security discussions. Another reason attackers love metadata is that it can reveal environment context that helps them move intelligently. Knowing the region, the instance identity, or the account context can help an attacker choose which services to probe next and which actions are likely to succeed. Even non-sensitive metadata can reduce the attacker's guesswork and shorten their time to impact. For example, understanding that an instance is part of a certain environment might hint at what data it can access or what permissions it might have been granted. Attackers also use metadata to confirm that they are actually running in a cloud environment and to tailor their actions accordingly. This is not about magic. It is about reducing uncertainty, which is what both defenders and attackers want. The difference is that defenders want predictability for safety, while attackers want predictability for exploitation. It is also worth noticing that metadata risk is often amplified by overly broad permissions assigned to instances. If an instance identity has minimal permissions, then even if an attacker steals its token, the attacker's options are limited. If an instance identity can administer large parts of the cloud environment, then stealing its token can be catastrophic. This is why metadata is tightly connected to identity and access management. Even though metadata sounds like a networking topic at first, the metadata service becomes the mechanism for obtaining a token, but the real damage potential is determined by what that token is allowed to do. Beginners sometimes focus only on how the token is obtained and forget to ask what the token can do. The calm, exam-ready approach is to evaluate both parts every time. Another subtle point is that metadata access can bypass some of the controls people expect to protect secrets. If a team avoids storing long-term credentials on disk because they know that is risky, they might feel secure. But if the workload can obtain temporary credentials from metadata, then a compromise still yields credentials, just through a different path. This is not an argument against metadata-based credentials, because they can be safer than static keys, but it is an argument for treating the workload environment itself as a sensitive boundary. If an attacker can run code or coerce requests inside the workload, the attacker can often get whatever the workload can get. That truth should shape how you think about workload hardening, segmentation, and the principle of least privilege. Metadata does not create the risk by itself. It makes existing privilege reachable. We should also address a misconception that metadata endpoints are safe simply because they are not reachable from the internet. Many attacks do not require direct internet access to the metadata service, because the attacker can ride inside the application that does have access. If an application accepts user input that influences requests, headers, or redirects, the attacker may not need direct network routing at all. The attacker only needs a way to make the application act as a proxy. This is why metadata is often discussed alongside web application security, even though it is a cloud infrastructure feature. It is also why defenders must think about internal-only services as still needing protection from untrusted input. Internal does not always mean trusted when untrusted users can influence internal behavior. To ground this, imagine a workload that serves user content and also fetches remote images to display in a page. If the workload will fetch any provided URL without restrictions, an attacker might provide a URL that points to the metadata endpoint. The application fetches it, receives a token, and then the attacker receives the token because the application returns the content. Once the attacker has the token, the attacker can call cloud APIs as the workload identity. Even if the workload itself was never supposed to share that token, the application feature created an unintended channel. The important lesson is not that fetching images is bad, but that features that make network requests must be constrained and validated. When you see any scenario where a workload can be tricked into making internal requests, think about metadata immediately. As we close, instance metadata APIs are popular with attackers because they provide a fast, low-friction path from a compromised workload to cloud identity and broader access. Metadata exists to make automation and configuration easier, and that convenience is real, but it also creates an internal interface that becomes valuable when the workload boundary is crossed. Some metadata content is harmless, but metadata that can return credentials or tokens turns the metadata service into an access broker. Attackers use it for leverage, speed, and environment awareness, often by abusing application behaviors that can be coerced into making internal requests. The calm way to approach this topic on the exam is to remember the chain. Compromise a workload, reach metadata, obtain a token, and then act according to the token's permissions. If you can recognize that chain and evaluate both metadata exposure and permission scope, you will be able to spot why metadata is such a consistent source of real cloud exposure.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.